Thank you, Dr. Salvetti, for your kind introduction. And I'd like to thank the organizer of the conference for the opportunity to give a keynote lecture today. And thank you all for coming to this session instead of the sightseeing in beautiful Florence. If some of you recognize my name, it is probably at the first author of this paper. So entitled The AIJ Guidelines for Practical Applications of CFD to Pedestrian Wind Environment Around Buildings. This paper has been cited by 1,600 papers on Scopus and 2,100 papers on Google Scholar. This paper was published in 2008 in JWEIA. Citations have steadily increased over time and are not limited to wind engineering. They included diverse fields and are interdisciplinary. I also served as associate editor in JWEIA. Last year, I was the guest editor for the special issue, 30 years anniversary of the first international symposium on computational wind engineering held in Tokyo, Japan. So this year marks 30 years later from the first computational wind engineering conference. AIJ Guidelines was published in 2008, just right in the middle of this 30 years. So in this lecture, I would like to talk about the application of CFD simulations to turbulent flow and dispersion in urban and non-urban environments in the viewpoint of the following points. How is CFD applied to environmental wind engineering issues? Why is CFD widely used in environmental field? What is needed for the future? First of all, I'd like to start with a short introduction of urban wind environmental issues. So, first of all, let's go back to about 2,000 years ago, not 30 years, because this is Italy. So the historical consideration of urban wind in urban environment explained in detail in these standard books. So Vitruvius, a Roman architect and engineer in the first century BC, he referred to a number of considerations for the design of buildings and towns in relation to wind. So he explained how Roman garrison towns were planned with a rectangular grid pattern of streets obliquely aligned to the harsh winter wind to reduce the chilling effect of those winds. Vitruvius' design features were later adopted in the 15th century by the Italian Leon Battista Alberti, probably everybody knows, who was responsible for the dissemination through France, Germany, Spain, and Russia. So he suggested careful selection of the site for building and settlements, along with a detailed study of the microclimate and materials to maintain heat and cold inside buildings, and to protect the space from the sun and the wind. However, after the Industrial Revolution, the new aspects of the relation between the city and the wind appeared. First, the invention of steel and concrete made it possible to build tall buildings and use space and density as densely possible. Second, the urban environment has seriously deteriorated due to the air pollution and poor housing. High-rise building created a new urban wind problem that is quite different from the previously considered relationship between a city and wind. So first, large wind loads. Second, wind gust on pedestrians. Of course, large wind load is a very important issue in wind engineering, but it's not one of the topic. The Flatiron buildings in New York was famous for its strong wind gust on nearby pedestrians. So it was widely known that the gust of wind generated by the building raised ladies' skirts. So policemen had to disperse the crowd of young people who gathered to watch. So additionally, the rapid urban expansion after the Industrial Revolution created the needs for regulations regarding the ventilation and lighting of dwellings in overcrowded cities. So the England garden cities of Letchworth and Welwyn have an industrial quota on the east side, so that the prevailing wind blows the smoke from the away from the city. Oh, sorry. What are the contemporary issues of urban and non-urban wind environments? So pedestrian wind comfort is still an issue. And the pollutant dispersion in building scales, called near-field pollutant dispersion, is a serious problem in the crowded urban area. And in snowy region, the interaction between snow and wind causes some problems around the buildings. And then aeolarian sound transport causes a severe problem in the coastal area and arid area. And insufficient wind also causes a problem like air pollution and urban heat island problem. The insufficient wind accelerates the urban heat island effect. So let's talk about the CFD. So how has been CFD applied to environmental wind engineering? So the computational wind engineering is primarily defined as the use of CFD for wind engineering applications. In the preface of the proceedings of first computational wind engineering conference, Chairman Professor Murakami stressed the importance of studying CFD as a technology uniquely targets wind engineering, and not as one borrowed from the mechanical and aeronautical engineering. So that's the important concept of CWE, I think. So please look at the cover of these proceedings. This picture is very memorable. So let me show a movie. So this is very preliminary, it's a very fast LES computation conducted by Murakami and Mochida and Hibi. So it's judged based on today's standard. It's rough, but it makes so powerful and appealing to us. So it had been quite shocking in 36 years ago. So Murakami in 1998 outlined the main difficulties in CWE. One, high Reynolds number. So high Reynolds number required a fine grid resolution, especially in near wall regions as well as appropriate wall functions. Two, complexity of flow field with impinging separation and vortex shedding, and so on. So this flow is highly three-dimensional and anisotropic, so it's difficult to model. Three, a sharp edge of rough body. So it requires careful selection for discretization schemes. Four, inflow and outflow. So appropriate boundary condition is necessary for inflow and outflow boundary condition, which are particularly challenging for LES. So how these problems being resolved? If so, how? So from now, I show my own review of the status of CW application in ICW conference. So this is the comparison of the total accepted paper for each ICW conference, and orange part indicates the papers using CFD in any way. So I call it CFD ratio. So it's a bit surprising. So I suppose the CFD ratio gradually increase, but not here. What happened in Florence? I bet all you eager to know. Find out. Here you are. Oh, sorry. So, first of all, I have to congratulate the success of the conference with over 600 papers. And CFD ratio close to 30%. This conference is most CFD-heavy conference ever. So, however, if we look at the field separately, we look slight difference. So, general topic, we cannot clear tendency. But environmental wind engineering, so the CFD ratio, the proportion of the paper used CFD is very high, close to 70%. In other hand, in structural wind engineering, so paper is very massive, but CFD ratio is not so high. It's less than 20%. So it's very contrast in this field. So wind energy is a new field in wind engineering. So the number of paper and the CFD ratio is not so high. And other topics, the CFD ratio is gradually increased. So why is CFD so often used in environmental wind engineering problem? So I reviewed the major achievement of CFD in environmental wind engineering over the last 30 years. So, of course, the computational performance has increased dramatically over the last 30 years. And in the early stage of CAWE, in-house code were used most often. However, more recently, commercial and open source CFD code have become popular. As you know, such change in the computational environment makes CFD more accessible. But only this not solve the difficulties. So I pick up the 4 major achievements in last 30 years: LES versus runs, and appropriate inflow boundary conditions, and verification and validation, and best practice guidelines. So LES versus runs is very classical topic in CWE. So turbulence, as you know, the main difficulty in CWE is caused by the very complex flow with high Reynolds number. So turbulence modeling is very serious point of the study. But as you know, the turbulence modeling can be classified to the 3 modeling approach: DNS, LES, runs model. So, but DNS basically difficult to apply to wind engineering problems. So LES and runs is the way to go. So in early stage of CWE, it was well known that the LES could reproduce good results even with relatively coarse grids. To this situation, Professor Fertiger stated that a few rather crude calculations indicated that it may be possible to obtain good results with relatively coarse grids, but these are too preliminary to permit final conclusion. If it turns out that LES can be done on very coarse grid, it will be one of the few times that nature has been kind to us with regard to turbulent flows. Fortunately, for some problems in wind engineering, nature is indeed kind to us. A key fact is that the large-scale organized velocity fluctuation dominate the overall flow structure around buildings in CW applications. So unsteadiness of large-scale flow structure caused by the interaction between atmospheric flow and the flow around the buildings is observed as vortex shading and intermittent flow in Street Canyon and so on. So such large-scale organized fluctuation should be distinguished from small-scale turbulence. So I explain a little more. So the difference between the large-scale organized motion and small-scale turbulence can be illustrated like this. The turbulence can be modeled by Rand simulation. The small-scale turbulence can be modeled by Rand simulation, but such large-scale motion cannot be reproduced by steady computation because such large-scale fluctuations are inherently different from turbulence. Even coarse grid LES can reproduce the essential flow structure as long as it can reproduce such large-scale fluctuation. But steady runs cannot reproduce it, thus inherently underestimate momentum diffusion around buildings. So these figures compare the results obtained by LES with relatively coarse grid and steady run simulation and experiments flow around the rectangular buildings. So you can see the run simulations very underestimates the turbulent momentum diffusion. Therefore, the largely overestimate the flow recirculation behind the buildings models. So the LES with relatively coarse grid can reproduce the basic flow structure and works well to some extent. However, the strong wind region near the ground surface, as known as the pedestrian wind comfort, is less sensitive to such large-scale fluctuation and can be predicted with high accuracy, even with steady runs model. So reversed caption models can improve the accuracy. As a result, the runs model are now widely used for such subjects. So Professor Brocken in 2014 stated that extrapolating the statement by Fertiger, I explained before, the pedestrian wind comfort is one of the few topics in the wind engineering where nature is kind to us concerning turbulent flows. So, however, the problem of runs underestimating momentum diffusion has a large impact on scalar transport. So turbulence mass flux is usually assumed to be proportional to mean concentration gradient, as seen below. This underestimation of momentum diffusion causes an underestimation of turbulent scalar diffusion. So this latter underestimation is often compensated by adjusting the turbulent Schmidt number. So this result is one of the collaboration with Professor Statspoulos. So this case, the building has gas release at the center of the roof. And this figure compares the time averaged concentration field on roof and walls. So the high concentration region appears upwind of the stack due to the reverse flow on the roof in the experiment. So this tendency is well reproduced in both computation. However, there is a large difference at the side wall. So in the steady runs, so the concentration is convected from the leeward wall. But LES and the experiment, the concentration comes from the roof by the horizontal diffusion. So it can be seen clearly in the instantaneous concentration field by LES. So the shape of high concentration region vary widely. And the plume dispersion around the buildings is highly influenced by large-scale unsteady flow structure generated by the buildings. So such large-scale fluctuations can be captured by LES, but not be reproduced by steady run simulations. So despite inherent shortcomings, LES has not been completely replaced by LES. So Professor Brocken summarized this issue in many aspects of building simulation for outdoor and indoor applications. The researcher and the practicing engineers have employed the increasingly available computational power to perform run simulations for large and more complex problems, rather than to make the switch from runs to LES for a less expensive problem. So what's happened in ICW conference about LES and runs? So this is the comparison of CFD papers indicating which type of turbulence model is used. So as you can see, the red line shows the LES ratio. So the percentage of the paper using LES. So generally, the ratio, LES ratio was increased. But in wind engineering, environmental wind engineering, so surprisingly, the ratio decreased. So in this sense, so it's in line with the interpretation by Professor Brocken. On the other hand, structural wind engineering, so the LES ratio generally increased and nearly 50% now. So the next achievement is appropriate inflow boundary conditions. So the traditional modeling of ABL in atmospheric boundary flow boundary layer in wind engineering has been based on the power or logarithmic law of the mean wind speed profiles experimentally and numerically. One of the major changes in the last 30 years is the increased attention to the horizontal homogeneity of the ABL over the computational domain in CW simulations. So Richard and Foxy were the first to point out that the inflow boundary condition and the turbulence model should be consistent for homogeneous boundary layer flow. So this paper has been gradually gaining recognition for its foresights, and thus its citations are increased. It's a bit surprising, so this paper was presented in the first CW conference, 1992. So later, the Professor Brocken in 2007 clarified the relationship between the sand grain roughness wall functions, which are often used in commercial code, and the horizontal homogeneity of ABL. So these findings has been widely used and extended in several follow-up studies. So this paper has been widely cited in many fields. So back to the chronology. So interestingly, so Richard and Foxy paper, it was presented in the first CW conference, and Professor Brocken's wall function paper was published in 2007. So just 15 years later. So inflow boundary condition, the setting of inflow boundary condition for LES are even more challenging because of the needs to provide fluctuating velocity field that varies in time and space. So this difficulty turns the attention of the community to the inlet condition, since they are directly related with reducing the computational effort while achieving accurate results for the velocity and pressure distribution. The setting of inflow boundary condition in LES will continue to be one of the major research topics at CWE. So synthetic methods in particular are expected to be a promising technique. However, the challenges are how to provide the necessary turbulence information and how to maintain proper turbulent fluctuation in the computational domain. Regardless of the chosen methods, it is important to balance the cost and accuracy requirements. So next, the verification and validation, V and V terminology, it became popular in last 30 years. Though for verification in recent CWE, systematic grid sensitivity studies have become common. The grid convergence index proposed by Roche is commonly used as an indicator to uniformly report the result of grid sensitivity analysis. For validation in recent CWE, qualitative validation using validation metrics is now widely performed. So frequently used examples as the hit rate, factor of 2, fractional bias, and normalized mean square error. In the validation process, the real world is replaced with a conceptual model. So here. So the conceptual model for CFD simulation of strong wind around buildings are relatively easy to construct using wind tunnel experiment as a representative of the real world. However, the urban environment is an extremely complex set of physical phenomena that must be abstracted into conceptual model. This is challenging and major source of uncertainty in CWE for complex urban environment. So in 2010, Dr. Franke comprehensively reviewed the established procedure and methods for the quality assurance of CFD codes and solutions and discussed their respective value for CWE. This paper is still informative and thus recommended. What are accuracy requirements? So the criteria for judging the V and V accuracy vary case by case and mostly depends on the research or application purpose. Quality depends on the accuracy requirements for the intended use of the model. So clarifying the level of accuracy required to perform CFD simulation is necessary. However, all possible uncertainties need to be considered for the accuracy requirements. So performing validation studies using validation metrics I mentioned before is not equivalent to evaluating the quality of the model. So Dr. Franke in 2010 papers suggests the accuracy requirements are different for different purposes and ultimately an engineering decision. The definition of acceptance criteria is not part of validation, but of accreditation or certification. So, the next, I would like to explain the best practice guidelines. So, in 1990s, the prediction and assessment of the wind environment around buildings using CFD became practical at the design stage. Knowledge in use of CFD for predicting the pedestrian wind environment are being accumulated in individual researcher as dispersed over individual publication in different journals, conference proceedings, and reports, but it was not integrated or standardized. So from a viewpoint of wind engineering, so some unreliable CFD results caused by inappropriate conditions and methods were reported. Based on this background, so in 1997, so a working group established in Architectural Institute of Japan. So AIJ is an academic society of architectural design and engineering. So the working group mission is to summarize the important point to be considered and clarify the application range when applying CFD to pedestrian, a prediction of pedestrian wind environment as a guidebook. Researchers from university and private companies have joined this project. This working group has been chaired by Professor Mochida for 15 years, and I have served for a long time as a secretary and chair. So AIJ benchmark, our original benchmark tests were created to investigate the influence of many kinds of computational conditions for various flow fields. And test covers scenarios from simple and building model to complex urban configuration. The wind tunnel experiments for validation were conducted by the members. So using this database, various sensitivity studies were performed, for example, turbulence model, discretization, computational domain, and representation of the surroundings. So at the almost same time period, so the very similar activity was started in cost action C14. This action was chaired by Professor Bori. And the purpose of this action is much broader, but it has the work package concentrated to CFD techniques. So these working groups, the activities is to identify the current R&D performed by members of the group that could benefit from coordination through the groups, and to validate the applicability of various CFD codes to wind engineering problems. The first outcome was the recommendation on the use of CFD in predicting pedestrian wind environment, edited by Dr. Franke and others. So in 2006, so CWD conference held in Yokohama, we organized the joint session for presenting each activities. And then the previous cost action is carried over to the cost action 732. The main objective is to improve an accuracy, the quality of mesoscale meteorological models that are applied for predicting flow and transport process in urban and industrial environments. So this action was chaired by Professor Schatzman. The member much include the meteorologist and physicist. So the outcome is the best practice guideline for the CFD simulation of flow in the urban environment, edited by Franke and others. So the same year, the guidebook contains the CFD guidebook for prediction of pedestrian wind environment around buildings were published. This guidebook contains the basic of wind engineering and CFD, and the best practice guidelines proposed by the working group. It also includes the computational result obtained by working group and their calculation conditions. So we also made available our wind tunnel database in online. So finally, 2008, so AIJ guidelines paper is published in JWEIA, and we can see the two important names in the acknowledgement. So Professor Statopoulos and Dr. Franke, who gave us a very valuable comment on the guidelines. So back to the chronology. So we can add the cost guidelines by Franke, 2007, and AIJ benchmarks also. So the first 15 years, so the various findings and knowledge of CWE from the early years were accumulated. And this knowledge organized and shared. And then the use of CFD for environmental problems has expanded based on the shared knowledge. So after the publication of guidelines, so our group continuously interacted. So a member of our working group, Professor Yoshie, attended the final workshop of COST 732. So now we are good neighbors in many papers. So this is the yearly trend of the citation of AIG guidelines, and the published papers contain CFD and wind and environment searched by Scopus. So the two trends are very similar, and the number have been almost equal in recent years. So the COST and AIG guidelines has significantly influenced by the number of publications in this field. So why is the AIG guideline paper cited so often? This is my personal interpretation. So first, the paper is in line with the social expectation that may arise. Second, since the working group membership was evenly split between the researchers of companies and academics from universities, a reasonable balance between practical and scientific consideration was achieved. Third, the pedestrian wind environment is a rare case where guidelines based on runs are easy to provide. That is, the topic is unlikely to cause controversy. Fourth, the experimental database for validation was developed and made available online. So I spent more time I expected, so I have to skip some slides. So after the publication, we continue the improvement of our best practice guidelines. So one point is the concerning LES. So in LES, we extend our benchmark tests. So we check the sensitivity of various conditions and parameters in LES for single buildings, and also check the effect of inflow boundary conditions. And then, so the sensitivity of discretization schemes for convection term in LES was systemically investigated. And so the findings obtained for the isolated building case were confirmed for more complex benchmark cases. So that in 2020, before the pandemic, so we published the revised AIJ guidebook in Japanese. So it includes our extension of the benchmark and guidelines. So this October, the Chinese translation of this guidebook will be published. Sorry for not English. So also we extend the benchmark database, and also provides the open database of fluctuating velocity generated by LES with whole wind tunnel geometry. So the new application example of CFD to urban and non-environment will be shown, but unfortunately time is short. So the Aeolian Sound Transport, yesterday, the very interesting mini symposium related to the wind-blown sound science and engineering. So several presentations use CFD, so including my own. So this is the unsteady run simulation for the sand surface deformation around the cubic obstacle. So it's compared with the experiment. So, and salt adhesion on buildings is my recent publication is very interesting. So the problem is the steel roof sections of large sports stadium built in the coastal area have incurred significant salt corrosion damage. So I have done the detailed airflow CFD simulation with the 3D-dimensional model of the stadium, and I calculated the concentration flux of the salt by using the detailed flow field analysis. So we can get the contour of salt adhesion for each wind direction, like this. So this is the deterioration level obtained by field survey, and we can obtain the very linear relationship between that obtained by CFD and field survey. So we can use this. It's effective to use this method for countermeasures such as changing the method and the intensity degree of salinity protection depending on the parts of structures. And it may be possible to devise roofs and or building shapes that aerodynamically control the salt adhesion. So finally, an issue for future consideration is pointed out. So extreme wind environment. So there is a concern that typhoons are becoming more powerful as the climate change. So CFD simulation suggests that the typhoon JB may have had instantaneous storm approaching 60 to 70 meters per second within the urban area of Osaka. So this type of extraordinary strong pedestrian wind must be considered. The effect of climate change are making the urban heat environment increasingly harsh. So annual number of heat-related deaths is increasing rapidly. So is there anything wind engineering can do? So the relationship to mesoscale weather condition is important when dealing with such extreme wind environment, especially when dealing with thermal factor. So in most previous study, large-scale meteorological effects have been simplified and then incorporated into CW calculation as a boundary condition. But however, some attempts have been made to consider more diverse and realistic meteorological effects on the building environment by coupling with mesoscale meteorological models. This flowchart is for the assessing outdoor thermal environment comfort based on CFD proposed by Mochida. So a recent study, the 3D and 3-day transient simulation of a heat wave in an actual urban downtown area, Montreal, Canada, was conducted using integrated CFD and weather research and forecasting models. So microclimate information is essential for identifying local hotspots with low wind speed and high temperatures. So urban ventilation in idealized city models has been investigated using CFD. So an air mass that takes a long time to reach a given region has a large mean age of air, which indicated poor ventilation. The case with direct wind angle, uppercase, had younger air and higher air exchange efficiency in the entire street compared to those for an oblique wind angle. This may bring to mind the aforementioned Whittle-Wills designs and how the rectangular grid pattern of streets, Roman garrison town, and the oblique alignment helped reduce the chill from harsh winter winds. But in harsh, hot environment, we must do the opposite. So finally, I conclude my presentation with a short summary, but I have not enough time, so please. Okay, thank you very much. So the wind environment in cities is a classical problem closely related to the shape and layout of buildings. So in the development of wind engineering, we have tried to achieve a comfortable and safe wind environment by controlling wind based on scientific evidence. CFD has been applied to wind engineering since the 1980s and has been recognized and utilized as an effective prediction and analytical tool, particularly in environmental field. So this is due to nature being more kind to environmental wind engineering than structural wind engineering concerning turbulent flows. The best practice guidelines and the validation database have played a significant role in the expansion of CFD in the environmental field over the past 2 decades. The application scope of CFD has been widely expanding not only to urban environments but also to non-urban environments. So because LES is intrinsically superior, its use will surely increase. However, the potential computational cost of LES is still too large for practical application that requires a large number of different analysis cases in a short time period. So ways to use runs wisely and effectively in environmental design should be explored, along with the accumulation of the knowledge on performing reliable LES. For this purpose, further expansion and enrichment of the best practice guidelines and open validation database are essential. This will be accomplished not only through the efforts of individual researchers, but also by international research groups and teams. So extreme wind environments associated with the climate change must be considered in the future, while appropriately incorporating large-scale meteorological effects. So even if CFD simulations are further advanced by new techniques such as AI technology, it is still important to be true to natural wind phenomena. So back to the chronology. So I anticipate the great paper will be published in the special issue of this conference. Thank you for listening.